different mechanisms to measure and so on. In our case, as I said, the assumption is a very, very basic assumption. I'm assuming this is a microcontroller software implementation. It's a pretty basic microcontroller. It's using left to right binary and modular exponentiation in the Montgomery representation. So it's going to take the message, it's going to get it into the Montgomery world, and then it's going to exponentiate it, and then it's going to get it out of the Montgomery world and basically send it. So yes, CRT, no CRT, doesn't really matter in this case. So next thing I am going to assume is a little part of the key. And because this is left to right, I am going to assume by induction that I know the left part, and I'm going from left to right bit by bit and guessing the keys one after the other. Right? So far, so good. The next thing I'm going to say is a little, this one is the bravest thing I'm going to do. And I'm going to say, pay attention here. I'm going to say, I am going to simulate the beginning of the encryption, the first few steps, right? And I know enough about the beginning of the encryption to know if there is going to be a Montgomery reduction in the next modular multiplication. And why is this? It's because the next modular multiplication is either going to be A times A, or it's going to be A times A. And I'll show it in more detail in the next slide. So I am saying that in some cases, there is going to be an extra subtraction, a very short operation called subtraction. And I'm hypothesizing that this little extra subtraction is going to make the entire measurement a little longer, on average, statistically. And I'm going to claim that I can measure this extra delay, and it will tell me if there was an extra reduction, yes or no. I can't measure it for a single variable, for a single calculation, because there's so much noise. But I can measure it for an entire population. So if I guess my key right, I can split my measurements into two sets. In one of them, there was a modular reduction, and the other one, there wasn't a modular reduction. And if I guessed right, then those measurements where there was a Montgomery reduction are going to take a longer time. Now, this is a very, very courageous and brave assumption. And why is that? Because this is a single subtraction in the beginning of the calculation. And after that, there are going to be hundreds, if not thousands, of multiplications and additional subtractions. And there's an entire modular reduction waiting in the end. And there's going to be some logic and transmission and so on. So if I don't want you to see that I'm wearing video conference casual, so I won't stand up. But if I were to say to walk from here to the window, it's going to take me, I'm going to say to measure how many steps it took me to get to the window. And from that, I will be able to deduce if the first step I took was a large step or a small step. So again, if I take a small step, I will statistically probably have to make, it will probably take me more steps to get to the window, but it's a very, very small contribution. So fantastic use of statistics, and I'll show you, I'll show it for you. So again, I'm not expecting you to understand this. It's a kind of a foundational thing, and it will take me, I think, a couple of weeks. Who here thinks that they already understood this offensive statistics method, Vaizata method? Who thinks they already understand it? Fantastic. Unexplainable. Wonderful. How do you understand it so quickly? Maybe you learned it somewhere else, probably, right? It's surely not based on my explanations, because I haven't explained it anyway. Yeah, so I'm happy that some of you think they understand. It took me several years to understand it as a master's student, and now I'm teaching it, so there you go. Fine. So let's do a timing attack on RC using Vaizata. First thing, we're going to assume that we're going to use modular exponentiation in Montgomery reduction. We're going to guess the leftmost bit of the key, and we are trying to simulate it a little bit at a time, and slowly we're going to get into the entire key. And I want to show you, I'm going to the shared notes now. I want to show you a little bit of my motivation. So I'm doing right. And I'm going to use what I have here below. Yeah. Go underline. Okay. So I have the message, I have the signing key, I have the modulus, I know R. I don't know the signing key, sorry, I don't know the signing key. I know the message, I know the modulus, and I know R. Why do I know R? Kirchhoff's. Or maybe I have the source code, I don't know. So I only know the first bit of the key. Okay? And S sub t minus 1, I don't know. Okay? I know S sub t, I don't know S sub t minus 1. So now I'm trying to simulate my, why do I know, by the way, S sub t is always equal to 1? Because otherwise, I could just start from the next one. So how do I do this? I can simulate the running of the left to right multiplication. So A is equal to 1. So far, so good, right? A is equal to 1. I can do that, right? Now, A is equal to A times A. I can do that. Great, I can do that. Next thing, A is equal to A times M. Why is this? Because S sub t is equal to 1. Right? I'll write this down. Next step is A times A. So each of these operations is done under the Montgomery representation. Cool? Now, the next operation, here I don't know what happens now, because I don't know the value of S sub t minus 1. So please, my magical autocomplete squad. Please fill in the values here. So if S sub t minus 1 is equal to 0, why don't you just flip these around? Thank you. You're magical autocomplete wizard. If S sub t minus 1 is equal to 1, then I have to do a multiply. And then A is equal to A times M. If S sub t minus 1 is equal to 0, then I skip the next multiply and I go straight to the squaring, and then A is equal to A times A. Now, notice that I know the value of A and I know the value of M so far. Of course, now I don't know. Now I have no idea. From here, I have no idea. But in this, there are two possible options for the next thing the computer can do. Now, I can run A is equal to A times M. I can simulate it. And I can also simulate A is equal to A times A. And as I am simulating, I pay attention and see whether is there a subtraction here. And is there a subtraction here? Maybe there is, maybe there isn't, but I can simulate. And this is the magic. So if S sub t is equal to 1, maybe there is a subtraction, maybe there is no subtraction. If it's is equal to 0, maybe there's subtraction, maybe there's no subtraction. But I can simulate it precisely. I can get an assumption, a hypothesis on what the device under test is going to do. Okay. So what do I do next? I'm going to assume. So I do this for a lot of possible inputs. And again, because M, a very important insight, because M is playing here, see that M is inside the equation. Because M is inside the equation, I can send a lot of different messages and get this calculation is going to do all sorts of random and crazy things based on my inputs. And this is in contrast to the square and multiply on the top, where basically I don't have a lot of control on what the device under test is doing as an attacker. But here I have wonderful ability to control what the device under test is doing. I can choose my hypotheses very well. So now I have measurements, and of course, after now I have no idea. But I'm going to assume hand-wavingly that this is random noise, which doesn't really affect my measurement. So now, I have a bunch of measurements, a set of measurements in which there was an extra reduction, an extra subtraction. And I have another bunch of measurements where there was no extra subtraction. And my ability to divide this into two sets depends on my ability to guess S sub t minus 1. If I guess correctly, then I split correctly. If I didn't guess correctly, then I didn't split correctly. And now I'm going to do some statistics and see if I made a reasonable split. And this is the magic of the Vaizata method. Let's see what's going on in the chat. Right, I think everybody's in good shape. So now we're going to do the attack in practice.